Hello, welcome to the talk entitled Reactive Web Services. My name is Kamil Szymański. I'm a tech lead at Pragmatic Coders. And today I'd like to discuss what reactive implementations are bringing to the table, what kind of problems they are trying to solve, and how they are trying to solve them. And we're going to focus mostly on three big pieces of the puzzle, which will be concurrency control, resources utilization, and backpressure. And this will be a live coding session, so let me get rid of the slides. All of the examples that I have will be on the Spring Stack using Project Reactor, but this shouldn't matter that much because the things that we're going to discuss will be things that are pretty universal, common to all of the reactive streams implementations. And all of the resources that all of the examples that I have should be fairly easy, yet I hope expressive enough. And let's get it started. We're going to start with something completely non-reactive, something that you should already be familiar with. This will be a Spring MVC-style web service, and it exposes one endpoint. And this endpoint, once it's been hit, it just sleeps for 1 second and returns some value. Now, as I've said, all of the examples will be fairly easy, but they will require you to run your imagination. So let's imagine that this sleep, this is some kind of a blocking operation. Treat it as a HTTP call to the upstream service, querying the database, reading data from the file, any kind of blocking operation. Now, what's important here is that it always lasts 1 second. So for the sake of the example, we ignore that there can be a GC kicking in. There's no operating system helping us. There's no caching involved. None of such stories. It takes 1 second and returns the value that we get from this blocking operation. Here it will be 42. And let's run this service. And I will have one question to you before it ramps up. What is the latency of that endpoint? Let's think about it for a second. At least second. Yeah, fantastic that this is at least second, not 1 second, because 1 second is only for the blocking operation. But we're good software engineers. We don't guess, we measure. So let's measure that. Yeah, let's kill the slides. And it's a bit more than 1 second, but it's only 1 second and more than 100 milliseconds for the first call, because there are some bits that need to be bootstrapped. For the first request or so, the consecutive ones should be way faster, more or less 1 second. And for the sake of the presentation, let's treat it as 1 second, because we're going to run a couple of semi-benchmarks. Those won't be proper benchmarks. We won't warm the JVM. We won't warm up the application. So focus on the rough values that those results oscillate around, not on the concrete examples. So this is not 1 second and 18 milliseconds. Treat it as 1 second. So having said that, with such an implementation, let's imagine that we have 5 concurrent users trying to hit this endpoint at the same time. How many TPSs, transactions per second, can we get with such an implementation, with 5 concurrent users? Any guesses? Although we don't guess, we measure. 5. Yeah, but let's check that. As we said, we're good software engineers. So what we're going to do, we will run Siege. Siege is a benchmarking tool. We will run it in a benchmark mode with 5 concurrent users, each of them doing 5 repetitions of the whole testing cycle, so that we get a bit more trustworthy results. And as you can see, we're getting HTTP 200s, and the response times are around 1 second. And we're more or less at 5 transactions per second. Now 5 is this theoretical maximum, and let's treat it like, as 5, although it's 497 for the sake of the example. Let's treat it as 5. So let's make it a bit more interesting. How many TPSs do you expect now? We've raised the number of concurrent users to 16. How many cores? So 2 CPUs are on hyper-threading. What results do you expect? Okay, so the question about number of cores is a good question, but not for this example, because right now we're not CPU limited by the number of cores. Although we haven't reached the 16 TPSs that we might have expected, we reached only 8 TPSs. And why is that so? It's because I've done something nasty for the presentation like that. I've set the limit of worker threads on our servlet container to 8. And if we get rid of this limit, we should be able to achieve 16 TPSs. So let's check whether we are able to do that. And looking at response times, we're going to be close to that. Yeah, 16 or almost 16. But let's imagine that we've set this limit for a reason. So is there a way, having this limit set to 8 worker threads, to achieve 16 TPSs with 16 concurrent users using that service? Is there a way? Okay, there's no way. Who's asleep? Yeah, there is a way, and it's about moving this blocking operation out of the worker threads. So what we can do, we can return, instead of string, we can return a callable here. I will tell later on how it's working, because it works on Spring. It doesn't work on other operations, other stacks, because this is part of the abstraction that Spring provides. So let me implement that. And I will explain what it does. So let's rerun it. Let's rerun the benchmark as well. And let's see whether we are able to get those 16 TPSs. The limit of 8 worker threads is still there, and we are able to get close to those 16 TPSs. And what's happening here is that we're returning callable. And under the hood, Spring uses the servlet's 3.1 capability, which is asynchronous processing of our requests. So what it basically does, it moves this blocking operation to some other thread that is executing it. The worker threads are only responsible for handling the request or getting the request. Then once it's like this blocking operation is completed, the response will be sent back to the client. And this is all good, but there's an important part that is missing here. Because we're offloading this blocking operation to some other thread, but we don't control it. We don't know how big this thread pool is it cached or not. And with such an abstraction, it's not easy, or rather it's impossible if you have multiple of such endpoints, to do that using just an annotation, changing the type, or something like that. Of course, we can get control over the thread pool that we are executing our operations over. So we can, for example, create an executor service. But we no longer can use the callable. We need to use some more technically advanced feature, like, for example, using deferred result sets, where we set some return values. We handle errors for any reason. We need to do that, of course, asynchronously, so there's completable future involved, yada, yada, yada. And if you take a look at this implementation, previously it was fairly straightforward. We just did our blocking operation, and that was it. And here, there's a lot of clutter. There's a lot of technical details. Like what we are trying to achieve here is hidden somewhere down at the bottom of all those technical goodies or whatever you call it. And this is not something that I would like to support in my software on production business facing software. Like, it's okay to do some technical involved stuff as a home project or just to learn something, but not to support such things on production. So is there a way to do that in a different way? And this is where reactive implementations can kick in. So let me just copy this implementation. We will do that in a new service, and we will do that because of one dependency that we added to our project, which is Spring Web Flux. Web Flux is an HTTP reactive aware HTTP component from Spring, and this will allow us to use reactive implementations like, for example, Project Reactor. So let's try to do that. Of course, we won't be using callable this time. We'll use the so-called mono. Mono is a reactive producer that is capable of producing up to one element. So it will be either 1 or 0 elements. And let's return a mono from callable. Okay. And let's run the service. We're going to check whether it works in a second. So let's run our benchmark. This time the port changes. And what results are you expecting right now with 16 concurrent users? It's reactive. It should be super fast. 1 TPS. So a pretty low value. Let's check it. So we're running that, and for sure it won't be 1, but it also won't be 16. It will be something around 4. Can you tell why? Yeah, I see that you've stumbled upon those issues. So what we have here is only 4 TPSs, and those 4 TPSs are related to how many cores we have here handling our request. And we have 4 cores. And why is it that we're limited to the number of cores? The answer is here. We're no longer running on Tomcat. By default, Spring Boot boots up on Netty. And Netty, it's not a servlet container. It doesn't run in thread per request model. It runs using event loops. And for event loops, it doesn't make sense to have more event loops that we have cores. Because we want to fully utilize those event loops. We want to fully utilize our CPUs. So if we would have more of them than we have cores, there will be a lot of context switching. Basically, we would lose a lot of computing power just for switching threads. So what can we do with that? Because what we've done here is something really, really stupid. We've blocked the event loop, which we only have 4 of them, or 4 threads running those event loops. we can do a similar thing as we have done previously. So what we need to do is move out this blocking operation out of the event loop thread. But there's a big difference in how to do that. If you remember from previous example, if we wanted to control what threads are executing those blocking operations, it was fairly technically involved. Like there was a lot of code, and the meaning, like what we are trying to achieve, was lost somewhere under all of those technicalities. And here, it is as simple as saying on what thread are we going to subscribe to those events that are going to be published by the reactive producer, which is Mono in that case. So we would say what scheduler, let's, for simplification, treat it as a thread pool, which will be handling those blocking operations. And we have a couple of them predefined for most of the reactive implementations, like there's an elastic scheduler, which means give me as many threads as I need. And those will be cached. There's a parallel which says there will be no more than the number of cores that we are having. We can create a scheduler from executor service. We have immediate, which means the same thread that is publishing items. There's a single and a couple of others. For the sake of presentation, we will use elastic. Although on production, consider using your own created pool, because the elastic one is not bound. So we can create an unbounded number of threads, or rather we are bounded with the memory that we are having. So let's rerun the service, and let's rerun the benchmark. So I hope that this time this will be close to 16 TPSs. And it is. And what reactive implementations are giving us in this example is the ease and relative safety of parallelizing our operations, moving them to different threads. This is really easy and relatively safe. Of course, we need to pay attention to what other things we are using under the hood, because if, for example, we are using thread locals, those thread locals, the context kept in the thread local won't be moved to the other thread that we are moving onto. So this is something that we need to pay attention to, especially if we are using a lot of transactional libraries, security libraries. A lot of them keep context in thread locals. It's possible to overcome that, but it requires us to say what context to move to which thread. But this is not the only thing that reactive implementations are giving us. So let me move to another example. And this time we won't be using Mono, we will be using Flux, which is a different kind of reactive producer. This is a producer that is able to produce any number of items. So it can be 0, 1, 3, 3,000, 30 millions, or even an unbounded number of items. And what we will be doing here is publishing documents. We will simulate this. So again, this is the part where your imagination should kick in. We are publishing an item each second, and we are taking first 9 of those items, and then we map them to a document. Of course, the numbers we are publishing are zero-based, so we make it indexed from 1. And this simulates publishing documents. And for the sake of the example, let's treat those documents as, for example, large PDF files. Let's say 1 gigabyte each. So what we will do is each second, for the 9 seconds or 9 documents, we will publish 1 gigabyte document each second. In total, 9 documents. And first, let's call this service. Let's check how it works. So we're hitting the service, and we're waiting, and we're waiting, and OK, we get some payload. Let me just pretty print it, and let's time it. In this payload, like this is not 1 GB because obviously it wouldn't fit even on such large screen. But what we're returning here is 9 documents, 9 GB of data, or rather we're returning a JSON array of those documents. And looking at what we received and looking at this implementation, I can see 3 problems there. The first problem is that although after 1 second we had the first document ready and it could be delivered to the client, and the client could have started processing it, we needed to wait for the whole 9 seconds to have all the documents published and serialized, and only after that they could have started being delivered to the client. So the time to the first document is the time to fetch or generate all the documents and serialize them. The second problem is that those are 9 documents, each of 1 GB. So we need at least 9 GB of heap for the payload only to have the service running. So the probability of hitting out-of-memory error is rather huge. And even if you have server large enough, like with a huge heap that is capable of doing that, there is still an issue on the client side, because even if we as a server publish that huge payload, the client might not be able to fit it into its own memory, to process it, to deserialize it. Of course, he can do some tricks to do that, but most of the clients don't do such things. So, is there a way to overcome those issues? Can you see any solutions to that, looking at the payload that we have here? I will give you a second. So I would say that instead of publishing the whole payload at the same time, we could deliver our documents to client one by one. So as soon as we have the first one published, we can start sending this document to the client. And this is doable. Let me sprinkle our implementation with a bit of magic. We will see whether it works, and then I will explain how it works under the hood, if it works. So let's rerun the service. And let's check whether it works and how it works. And what we can see here is that each second we're getting the documents delivered to us one by one. So we are not sending to the client the whole array of all the documents. We are sending one document after the other. And there was a bit of magic involved here, or rather Spring abstractions. How it works under the hood? Once we get the request from the client, we open the connection and we start publishing those documents. Once a document is generated, we serialize it, we flash the response buffer, so bytes start flowing to the client, but we don't close the connection. So after the first document is sent to the client, the second one is published, we also flash the buffer and wait for another document to be generated, and so on and so forth. After 9 documents, the reactive producer, the Flux, will say to us, I'm done. I won't publish anything more. So as soon as we have all the bytes delivered to the client, the connection, HTTP connection, will get closed. So again, this is not some magical solution. This is something that we've been using for a long time. I remember doing such things using Comet Bayou in like early 2010, 2011, something like that. It didn't work flawlessly. There was a lot of issues with that. But again, the solution is not new. What's new is the ease of use provided by the abstractions built on top of reactive implementations. And this is fairly simple to use and relatively safe. But going back to the problems that we had. The first problem, the time to the first document, I would say it's solved. As soon as the first document is published and serialized, it starts being delivered to the client. The second problem, having to fit all the payload on the server side, I would say it's also solved, because we no longer have to fit all 9 gigabytes on the heap. We can do that one document after the other. However, on the client side, this might not be solved yet, because if the client is faster to consume and process those items that the producer is able to produce them, then we have no problem. Like the client only needs to fit one document at the time into memory. If he's as fast as the producer, the same story. However, if it's slower, then the probability of out-of-memory error is pretty high, especially if it's way slower than the producer. So to overcome that, reactive implementations have the so-called backpressure. And because we are running on HTTP protocol, HTTP 1.1, this is a protocol of request response. There's no channel of communication from the client to the server other than sending the request and waiting for the response. So on HTTP 1.1, I won't be able to demonstrate that. So for that reason, I have another example, which is a standalone application that will allow me to demonstrate what backpressure is. So first of all, let me run the service and tell you what it's doing. So what we have here is a document repository, and this document repository fetches all the data from the repository. This repository returns a flux of documents, so it returns a reactive producer capable of supporting backpressure. And we have 9 of such documents. So there will be 9 documents to be processed. And then we subscribe to those documents. First, we log that we are starting to process it. Then we sleep for 1 second. And then we log that we finish processing it. The important part here is the logging on warning level and info level, because the IDE colors it in different colors, so that it's easier to grasp. And the backpressure, it's mostly described as a way for the customer to say to producer that he's too fast and he needs to slow down. This is a huge simplification. So I will go a bit deeper into that. However, there will be still a huge simplification here. So backpressure is a strategy of dealing with the pace of how frequently events are being published, or saying to our producer how many events do we want to get published at the time. And we can use a lot of those strategies. So we can say, for example, to buffer, to drop all the events that we are not able to process, to error out, to drop everything besides the latest one. However, we will dive into the protocol that is there, because from this description, you might have probably noticed that it's about 2 actors. There is a producer producing those events, and there is a subscriber subscribing to those events. And there needs to be some communication channel between them, so there is some protocol. But before we dive to this protocol, let me show you a couple of interesting things here. So, as you remember, we were previously able to move those blocking operations to different threads. So one might expect that if we do things like that, it should parallelize this subscription and process all of the documents at the same time. And this is not the way that it works. Sorry. As you can see, those documents are processed one by one, sequentially, and they are being processed by the same thread. And this is because subscription, by design, is sequential. So it will always happen on one thread. Of course, if we don't try to hack it, and we will try to hack it a bit. So what we will do here is we will move this logic to a different class, and we will add a bit of hacks there. So let me move to the class. This is a class that I have written, and this class does two things. First of all, it hooks into hook onto next hook method. And the other thing is it splits the implementation, introducing the mono here, so that we will be able to parallelize the subscription, because the only sequential part will be publishing, creating this mono, this reactive producer. The subscription to this reactive producer will happen on different threads. But back to the protocol. So what we have here is a hook on next method, which is pretty much self-explanatory. It will just process the element that is being delivered to this subscriber. However, let's try to hook into some other hook methods. So what we can do here is tell what to do when we complete processing all the documents, what happens if there's an error, what happens if we cancel the subscription, and what happens on the subscription part. So once we create a subscriber and subscribe to the publisher, let's check how the default implementation looks like. And what is the default implementation is to request for a long max value of elements. Although it's not true, it's not a long max value or the value of this constant. It's a so-called unbounded request. So what it says is, hey, producer, give me everything that you will publish. So if there's just one element, give me one element. If there's like gazillions of them, give me all of them, even if it's a value larger than long max value. So let's try to play a bit with that. So instead of doing the unbounded request, we'll request for one element. What do you expect to see if we run this example? We have 9 elements. And on subscription, we ask for 1. Let me run it in the meantime. So we asked for 1, and we got 1. And that's it. This is the end of the story. If we asked for 2, we'll get 2, and then that would be it. We're getting 1 on the second one, and no more of them. So what we can do is, as soon as we process the item that we had, we can request for another one. So if we do that, then we should end up with having processed all 9 of those documents. And this is exactly what it's like. So let's try to do that in batches of 2 elements. So each time we are requesting for 2 elements, and as you remember, this is all sequential. So this is a place when we hack a bit, hence this mono. We will schedule that on the Elastic scheduler. And although we are asking for 2 documents, it's not that we will process that in batches of 2. It will be in powers of 2, because first on subscription we ask for 1 document, and then after each one of them is processed, we are asking for 2 more. So once we process 2 documents, each of them will ask for 2 more. So it will be powers of 2. Can we somehow fix that? Yep, we're able to do that. And I have an implementation that allows me to do that. It's another class of mine that I have written. And this time, it uses a bit more of lower level concurrency primitives. It uses some atomic integers, and each time a document is processed, it checked whether it processed all the documents in the current batch, and if it's so, then and only then it asks for another batch. And if we run it, this should process documents in 2-element batches, and this is exactly the way that it works. However, as I've said in the beginning, reactive implementations allow us to do that in a safe and easy way, and reaching back to those low-level concurrency primitives, to atomic integers, references, cyclic barriers, and so on and so forth, is not the way to go. So if we stumble on the implementation like that, we should think whether it's possible to do that in a different way. And of course, it's possible because most of the reactive implementations come with a plethora of operators that allow us to do that. So we could, for example, parallelize it and say that we want to parallelize up to 2 elements. Of course, we need to say what scheduler will be responsible for processing that. And with such an implementation, we should end up with being able to process elements in 2 elements batches. And exactly this is the way it is. However, till now, we only looked at 2 parts, like how the protocol looks like between the producer and subscriber, and how it's handled on the subscription part. Now, let me move on to the part of the producer. So what I would like to do right now is to check whether the publisher is really supporting backpressure. So if it allows me to load only as many events that I am able to process, and since the subscription is sequential, I would like to load those documents one by one. And although our repository, it returns Flux of documents, so a producer that is capable of supporting backpressure, it doesn't mean that it supports backpressure. So let's try to check whether it supports backpressure. And for that, I have a simple test that involves debugging, but it's not as hard as it sounds. This debugging session will be fairly simple. What we need to do is just place 2 breakpoints. First one, when we fetch all the data from the repository, and the other one for the logic that is processing each of those documents. So let me run a debugger. And let's check whether our repository implementation really OK, the debugger is on. And those 2 breakpoints we have here only to catch the snapshot of what's on the heap. I'm using the memory view in IntelliJ. And here, we are fetching all data from the repository. However, since we are processing items one by one, I would expect to have only one document loaded here. So let's resume processing of our code. And we can see that that we have 9 documents. So we have all of the documents that are in the repository already loaded into the heap. So although that we are returning a producer that is capable of supporting backpressure, it's not supporting it. And let's check why it's that. So what we are doing here, we're creating this producer from the structure that is already on the heap. We're creating that from the iterable, or rather from the list that is already on the heap. So what we could try to do is create a Flux from a stream. And the question here is whether that would make it work in the backpressure supported way. So I would say it won't. I won't run it because once I explain it, this should be fairly obvious. It's not possible because we are creating a stream from the structure that is already on the heap, because here we have a list that is already on the heap. And in JPA 2.1, it's not possible in the plain JPA. In JPA 2.2, there's a stream method added to entity manager that allows us to open stream. But here we are using JPA 2.1, so let's try using still JPA 2.1 to overcome this. And as I've said, in plain JPA, it's not possible. So let's instead use Hibernate, which is a specific implementation of JPA. And let's rerun our debugger. And let's resume. Like the first breakpoint is here only to catch the snapshot of the heap. And let's document. And we can see that we have only one document loaded on the heap. If we resume, we should have two documents. Like in the latest versions of IntelliJ or the plugin, we need to just change the query here. It doesn't auto-refresh. And we can see that we have two elements on the heap because one more was loaded and so on and so forth. So for the third element, we will have three elements on the heap. And one might think that at some point of the time, there will be a garbage collector kicking in and garbage collecting all of the already processed documents. However, it won't be the case, because what we are dealing here with are managed entities. So they are not able to be garbage collected, because they are still in the O1 cache, level 1 cache. And to overcome this, we should either use the Hibernate support from scrollable result sets, so the ones that do not deal with reactive implementations, or we could use plain Jdbc, which is something that we will do in a second. However, let me do one more thing, because this is really interesting. If we run it on top of Hibernate, there is an important thing: how many queries are we issuing? Because we are processing documents one by one, but it doesn't mean that we will issue that many queries that we have elements. So let's check the logs. And what we can see is that there is a single query here. This query happens here when we fetch all the documents from the repository. It's just that this query opens, for example, a cursor that goes over those results. So there's a lot of network hops, because we are fetching one element or how many elements we want to the heap. And if we run out of them, we need to go back to the database to say, give me more of the results. However, still, there is a single query involved here. So let's check how it could work on plain Jdbc. Or rather, before we do that, let's check how the Hibernate implementation looks like. So in Hibernate, we just open a stream over the query, so something that is added to JPA 2.2, although the API looks a bit different. And then based on this stream, we create a Flux, this reactive producer. However, there is another important thing here. We also say what to do on terminate. So once there's an error, or once we run out of the items to be produced, in that case, we should close the stream to not leak the resources, not leak the connections, things like that. And having said that, let's check how the Jdbc implementation could look like. So this is a fairly large implementation, but it's not that complex. We are starting with obtaining the connection from the data source. Then we set auto-commit to false, just to be able to, for example, open a cursor over on the database side. Then we create a statement. We can set the fetch size, so we do not have to do those network hops for each of the items that we will be fetched from the database. We can fetch it in batches like 5 of them, although we need to remember that it's just a hint for our DB driver, and the DB driver can ignore it. It might not make sense, for example, if we are running H2 in database, because it's in memory, or if we are running that in memory. And then we create a query, and from this query we get a result set. But the result set, it's not a structure that is completely on the heap. The result set is just a pointer to a result in the results that the query is returning. So it will contain data from just a single row from the database. And from this result set, we create an iterator, and out of it, we create a Flux, this reactive producer. And also an important thing, on termination, so when there's an error, or if all the documents are already processed, we close the DB connection to not leak connections, resources, and so on and so forth. Converting to Iterator is rather straightforward. It's just checking whether there's something more in the Iterator. However, there is an important thing here, how to convert the row that we get from the database into our domain object. And this is why we do not have something like Spring data supporting relational databases to publish, to return reactive producers, because here we need to go deep down into like ints, strings, and other types that are persisted to the database, and we need to map them to our domain domain object. And it might be a bit of time that we get to see those implementations. However, Oracle is working for an alternative to Jdbc, a specification that will be Jdbc-alike but non-blocking. So it will allow us to do the reactive like interactions with databases. But there will be a couple of years until we see it on production. So if you really need to do that, think twice, because this is really low-level stuff. If you don't have a really low latency requirement, do not dive into that area. And to summarize what we have gone through is the reactive implementations are not new ideas. Those are pretty old ideas, but they are wrapped in really cool, readable, and safe APIs that allow us to easily use that. Of course, it's not all beautiful, because as you know, in IT, everything is a trade-off, so and those abstractions are leaky, so we need to watch out for example, thread context like thread locals. If we are switching threads that we are using, we need to also pay attention to how our implementations looks like. So what we are returning here is not a document, it's a Flux of documents. So if our domain is all about customers, orders, and payments, in our domain, we won't be speaking customers, orders, and payments. Those will be fluxes of documents, monos of payments, or if you are an RX Java fan, those will be flowables of orders, singles of customers. So this changes our APIs, and this is a huge deal, so you should consider whether you want that or not. And although it impacts the way you code, I would really encourage you to check out the reactive implementations, see whether this approach solves your issues, and if it does, only then evaluate whether solving those issues is possible only with reactive implementations, probably not, and whether it makes sense to use reactive implementations or use the older approaches to that. And with that, I run out of time, so I would like to thank you for attention and wish you the great rest of the conference. If you have any questions, I will be here, so don't hesitate to ask any questions. Or